the worksheet print is a little bit too small. So let me do example 3 and example 4 in the notebook. Okay, so let's see if n factorial divided by 3n factorials converges. What do you think? I think probably it does, but I'm not sure. Okay, so let's compute a n plus first. It's going to be n plus 1 factorial divided by 3, and we have to multiply 3 by n plus 1, right? Okay, so what we get here is 3n plus 3 factorial. So this is going to be n plus 1 factorial divided by 3n plus 3 factorial. Now we will be comparing 2n factorial and 3n factorial. So we want to rewrite this piece as n factorial times n plus 1, and then downstairs piece is 3n factorial, and then times 3n plus 1, and times 3n plus 2, and also times 3n plus 3. Okay, so if you are not convinced, try substituting some number for n, let's say 2, and then find a n plus 2, so n third, right? And see if this is what you get. Okay, so then rho is going to be the limit n goes to infinity, a sub n plus 1 divided by a sub n, the whole thing is absolute value, so we get limit n goes to infinity, and I'm writing down from here, n factorial times n plus 1 divided by 3n factorial times 3n plus 1, 3n plus 2, 3n plus 3. This is my an plus first, and then I have to multiply by flipped anth. So I'm getting 3n factorial divided by n factorial. Now time to cancel stuff. So I'm cancelling the factorials, and I'm getting actually a much nicer thing, because for this term I can factor out 3, and this is 3 times n plus 1, right? So I can further kill n plus 1. I'm sorry, cancel. Well, it's not live. You can't really kill it. Okay, and then I am getting the limit. Everything is positive, so I don't have to worry about absolute sign. So I'm getting 1 upstairs, and downstairs I will have 3n plus 1 times 3n plus 2, and times I'll only have 3 left, having cancelled n plus 1. And I definitely have quadratic equation downstairs and nothing but 1 upstairs, so this limit is going to be 0. It's less than 1, and therefore by ratio test the series converges. Okay, then we have to do example 4 that is put here to convince you that when you get rho, when you compute rho and you get 1, you can have all kinds of behaviors, convergence and divergence. Okay, so let's consider series n is equal to 1 to infinity n squared, for which rho is going to be 1. Let's check this. Okay, so for this series, rho will be the limit n plus 1 squared divided by n squared, n goes to infinity. Let's open parentheses. You already see where it goes, right? We will have n squared plus 2n plus 1 divided by n squared. So we are getting the limit n goes to infinity 1 plus 2 divided by n plus 1 over n squared, and this is going to be 1, right? So when we're looking at the ratio test, we know that it's inconclusive. But when we just look at the series, we can see that it diverges. We can use divergence test to prove this. So, or just obviously you are adding greater and greater numbers, right? Okay, another example with rho is equal to 1 will be a series n to the minus second. So we will have series 1 over n squared. N is equal to 1 to infinity. No, just believe me that we will compute rho for this series. We will get 1 on one hand side. On another hand side, what do we know about this series? It's a p-series. P-series, and it converges, right? Converges because p is equal to 2. And every time that p is greater than 1, the series converges. So when rho is equal to 1, you can have convergent behavior or you can have divergent behavior. So what you say is that the ratio test is inconclusive and you have to resort to some other means to find a convergence or divergence of the series.